My favorite ride at Disneyland is Mr. Toad's Wild Ride. Have you ever been on Mr. Toad's Wild Ride? I don't have like a very high tolerance for insanely crazy roller coasters and stuff. So I just like Mr. Toad's Wild Ride just because it's so bizarre. All right, but I thought, what would if I could design a ride for an amusement park, what would it look like? So this would be it. Now, here's what's really magical about this, about my roller coaster. My roller coaster is not going to have any friction in it. Zero friction. So here's the level ground. We'll measure gravitational potential energy. That is, we'll measure all our heights from the ground. So here, the height would be 0 if you're standing right here. And so, here are some people. Here's a little roller coaster car on a track, like so. And there's a couple people in it. Here they are. They got their arms up. They're very brave. Okay. And what happens on this track is that they go up a bit. They get pulled up quite a steep hill, and then they are at rest at the very top of this hill. I want them to just barely come to rest at the top of the hill, just to build the suspense, before the ride starts. And then they go, down steeply this first hill, and then they reach the ground, and then they go up a little hill, and then they go down the little hill back to the ground. And then when they get here, there's a brick wall right here. Okay. Now, to avoid any possible lawsuits, and that's my main concern is getting sued, is I'm going to put a stop right here with a spring. Okay? So this spring will prevent them from hitting this wall too hard. Now, what I want to do is look at this in terms of energy diagrams. And here I will kind of use the book's convention. Instead of using final and initial, I'll use 1s and 2s, but I'm going to use 1s, 2s, 3s, 4s, and so on. So I'm going to call, this is state number 1. Here you're on the ground, and you're not moving. Then someone's going to pull them up here, and then they're on the top up here. And, excuse me, they are, and I'm going to call this state number 2, or position number 2. So therefore, their height above the ground would be h2. And that's what I'm going to use the 1s and 2s as subscripts to describe where I am on my ride here. And then they're rushing down the hill. They say they're about halfway down the hill. Whew. Okay. And we can show their speed by showing little streak marks. Okay. Then they're back here on the ground. And remember, there's no friction in this ride, so they're really moving now. They've got lots of velocity. So this will be state 3. This will be, 4. Then they get to the top of this little hill again. Okay, we'll make that 5. Then they come back down, and let's say that when they hit, they squish in this spring and come to a stop. So here we'll show them, maybe the spring is compressed at this position, and so at that position, they're stopped. So that'll be 6. And now I want to look at this in terms of energy and conservation of mechanical energy. At position 1, okay, they're not moving, and they have no height. If they're not moving, they have no kinetic energy. If they have no height, they have no gravitational potential energy. They've really got no mechanical energy. So at position 1, it looks like this. This is kinetic energy, and this is potential energy. But then what happens is, and you've been on a roller coaster before, right? And what do? You sit in this little car, and then they haul you up to the top of the first hill. Now, except for California Screaming, which is really a cool one. On California Screaming, they shoot you at the bottom, and then you coast up to the top. But in this one, this is more standard. What they do is they have a generator, or not a generator, a motor, electric motor, and it turns a system of chains, and this is hooked to the chain. And what they do is they do work on you to haul you up to the top of the hill. Now, in your kinetic energy container, they got to get you moving a little bit, right, to go up to the hill. Is that right? So they're going to add a little tiny bit of work to give yourself a little tiny bit of kinetic energy. But it's really not very much, because you're not moving very fast when you're going up to the top of that hill. But what are you gaining a lot of as you go to the top of the hill? They're adding a lot of work. This object right here is adding energy to your system. Where does that energy come from? Well, if it's electric, it comes from the grid, which is connected to a power plant somewhere. All right, but some outside agent is doing work on the people in the roller coaster car and hauling them up to the top. So that's what these little arrows stand for, is the work. So this was at state number 1. Well, at state 2, what have we got? Well, we come to a stop. So all that little tiny bit of kinetic energy that they gave to get us moving is now gone. And so what we did was that the work done turned essentially into oops, I didn't need to do that. Potential energy. And then we'll go ahead and show the kinetic energy like this. But now you're up at the top. So at this position right here, all your energy is potential energy. You don't have any kinetic energy yet, right? Now, this energy came from the work done that got poured into here, and now it's here. And so this is at state number 2. But then what happens? You get a so slight nudge. We'll ignore the energy added from that slight little nudge. And now you start rolling down the roller coaster. And what's happening? Gravity is doing work. We're going to pretend there's no air resistance or anything. It's a coaster. That means gravity is pulling you down. So gravity is doing work. So what we're doing is we're gaining kinetic energy, right? Does that make sense? We're going faster and faster, so we're gaining kinetic energy. But where is this work coming from that's allowing us to gain kinetic energy? It's coming from our gravitational potential energy. So after you get that little nudge, we start losing gravitational potential energy. Gravity's doing positive work, and therefore changing the kinetic energy, increasing the kinetic energy of my roller coaster. So now let's draw the picture at state 3. At state 3, about half of my gravitational potential energy is gone. But I have about half of it left. Where's the other half? It's now in the kinetic energy. So here's my potential plus kinetic. But what do we notice about the total amount of energy? It's the same. So if I pour half of this into here, the total amount of energy is the same. When I get to the bottom of this hill, I have no more gravitational potential energy. All my energy is now kinetic. So we finished pouring it in here. So this is empty now. And there we are at state 4. But what do we notice about the total amount of energy? The total amount of mechanical energy is conserved. Okay, then we go up this little hill. Now what's going to happen as we go up the little hill? Gravity is going to slow us down. Gravity is going to do negative work. Negative work means we're going to take that kinetic energy away, but something has to happen to that energy. And where is it going? Yeah, what's happening is that as we go from 4 to 5, we're going to start pouring this energy in here. We're going to lose kinetic energy, but gravity is now doing negative work, which means I'm adding gravitational potential energy. And when I get to state 5, I've got, well, it's a little less than half way up, so I've got this much potential energy. Still got most of my kinetic energy, maybe a little bit more than half. But if I were to add these two together, it would equal this one right here. So this is state 5. Then it hits then it comes down here, it's got all its energy, it's all kinetic again, but then what happens? It hits the spring. The force applied to the spring is to the right, but the force that the spring applies to the roller coaster is to the left, and what we care about here is the work done on the roller coaster by the spring. So the spring applies a force to the left on the roller coaster, but the displacement is to the right. When the force and displacement are in opposite directions, we're doing negative work, which means we're taking that kinetic energy away. Where is that kinetic energy going in state 6? We now have a new container. We don't have any, and let me add a G to all these U's. I should have done that in the beginning. This is gravitational potential energy. Well, when you're down here, gravitational potential energy is 0. But I've stopped. So my kinetic energy is 0 as well. But what have I got? I've got a different kind of potential energy. The potential energy stored in a compressed spring is U sub E for elastic potential energy. And all that energy is here. Okay, and so this is state number 6. Now there's another way of putting this that's a little bit easier than drawing all these little diagrams, is that, well, the energy down here is 0, but we're going to do work. And so we're going to apply a net force, we're going to do work, and the work done by that net force is going to give us all the energy we need. And that's going to be equal to the mechanical energy And I'm going to use the capital letter E for mechanical energy. It's E2. All the work I did is going to be equal to E2. Then we rush down to E3. To 3. But what's true about the total amount of mechanical energy at 3? It's equal, it's equal to E2. And at position 4, and at position 5, and finally at position 6. So the work done by the net force to get you up to the top of the hill here is equal to my mechanical energy everywhere else in the problem. Now what's this spring going to do unless it latches somehow? It's going to bounce back. And so you're going to go backwards and then back up to the top here. Now let's say that there's a little pebble on the track or something up here. Then what's going to happen? It's going to let you kind of come back. Then you're going to go back. And basically, here's why this ride is so awesome. It never stops. You get your money's worth from here. In fact, you may get tired of it after a while. You might want to bring some food with you or something. You could spend eternity on this ride. Okay, because in this magical ride, there is no friction. Now, of course, in reality, there is a little bit of friction, and what that friction is it's a loss of energy. And we'll talk about that. We're mainly going to talk about that when we get to chapter 12. Talk about thermodynamics. But let's say that for a short period of time, maybe a couple of oscillations, just like with the pendulum we looked at, that we can ignore friction. The losses due to the energy losses due to friction. This lets us set up a problem. Let's say you know what E2 is. And you want to know, let's say here's H5. That's the hill, that's the height of the hill. What if you say, okay, I know what the height of hill 2 is. I know what the height of hill 5 is. How fast am I going when I'm at the top of that hill? Now, if you're a designer of roller coasters, that's a question you're going to want to know. How fast are the roller coasters going to be at the top of that hill? You want to make sure it's not so fast that you come off the tracks. Or if you are going to come off the tracks, what are the G-forces on the passengers? I mean, you want these people to have fun. Okay, you don't want them to suffer brain damage or hate the ride or whatever. So you have to know how fast these things are going. This gives us an easy way to do it. By the way, there is no way to use kinematic equations to figure out what the velocity is here. You can't do it. It's too, there's all these curves and the forces are changing. The accelerations are constantly changing. So you can't use kinematic equations when the acceleration is changing. And so there's no way to use all that stuff we did earlier in the year to figure out what the velocity is here. But if you assume that mechanical energy is conserved, it becomes an easy problem. Because everywhere in here the energy is conserved. So you say, E2 is equal to E5. That is the mechanical energy here is equal to the mechanical energy here. And say, well, what is E2? Well, mg h2, where h2 is this height. Now, what is the energy at position 5? Well, it's mg h5. Now, what's that? That's the gravitational potential energy. But what else have we got? We also have kinetic energy. Now V5, notice that subscript is there to identify where we are on the ride. Now, this gives me an equation that allows me to solve for velocity. Notice there's something the same in every term. What's the same in every term? The mass. That's why the mass doesn't matter. You can put, on one little roller coaster car, you can put little kids. Okay, and then on another roller coaster car, you can put the biggest, beefiest people you can find. And they're going to be going the same velocity when they get to the top of Hill 5. So the mass goes away. And now I can solve for V5. It's just a little bit of algebra. I'll do it in one step. But, you know, it's V5 is equal to, well, you got to subtract this from here. So this is going to be G times H2 minus H5. Okay. And then what are we going to do? Multiply by 2, and then we're going to take the square root. And this will tell me what the velocity is, my speed anyway, at the top of Hill 5. But this is just, going from here to here is just algebra. And I'm going to assume you can do that. The physics of this problem is recognizing that the mechanical energy is conserved. So my mechanical energy here will be equal to my mechanical energy here. And then you recognize, okay, right here, the only kind of mechanical energy I have is potential. I don't have any kinetic energy. The kinetic energy container is empty. But that's going to be equal to the mechanical energy here, where they are shared between gravitational and kinetic. So you write out the equations for potential, kinetic, and solve for your unknown. Now maybe I give you the velocity. Maybe I give you the velocity and I ask you to solve for how high is this hill. Well, then you just solve for H5 instead. Subtract, figure out what this energy is, subtract it over, you know, divide by G. Okay? So, and by the way, don't let the algebra side, you know, please just take your time and do the algebra one correctly. Okay? In fact, that's, you know. But anyway, so this is the ride. Any questions? All right. So you're going to be given a lot of problems where mechanical energy is conserved. How do you set it up? E equals E. That's what conservation of energy means. The energy I started with is equal to the energy I've got wherever I am. And then you break that down into where is the energy? Where is the energy? Oh, it's shared over here, but it's all in one place over here. And that, if you've set it up correctly, it just becomes algebra 1 after that. Okay, that is all.